Hey guys, welcome to the Curiosity Channel. This is a really small horse. It's even smaller than the smallest living horse, Thumbelina, who's only 43 centimeters or 17 inches tall, barely knee-high. But it's really easy to find things smaller than this toy horse. For instance, a mint, an ant, a speck of dust, an atom. But that leads us to an interesting question. What is the smallest possible thing? Scientists and philosophers have been theorizing about this subject since the dawn of time, primarily wondering if there indeed was a smallest possible thing. What if I could take a grain of sand and just keep dividing that in half onto infinity? Would I ever reach the end of it? We've known about atoms and subatomic particles even smaller than atoms for quite some time, but at this point, what's to stop me from assuming I can just keep dividing into smaller and smaller particles? What if those elemental particles are just the smallest ones we've so far discovered? Let's look at the question from a different angle. Space. Does space have a smallest gradation? Imagine space were like a sheet of graph paper, and the space between each lines is the average size of an atom. Well, that's not going to be small enough because we know that atoms are composite subjects. They have smaller particles that make them up. So let's add a few more lines onto our paper. Now the space between each line is the distance between the nucleus and the electron of an atom. Well, even that's not going to be small enough because the electrons, the smallest of those atomic particles, are made up out of even smaller particles known as quarks. So if we add enough lines onto our paper to accommodate the quarks, well, even that's not good enough, because what if I take a quark and scoot it over a little bit? If I don't have any lines there to show the new position of the quark, I've got details in space that I don't have gradations fine enough to show. So every new position of these quarks is going to matter. Or is it? The size of an object is defined simply by the amount of space that it takes up. So before we can answer the question of what the smallest possible object is, what we need to do first is answer the question of what's the smallest amount of space that matters. But how do you determine what amount of distance matters on such a scale? I mean, if you scooted my coffee cup 27 proton widths to the right while I was in another room, I probably wouldn't notice. I mean, that kind of distance is imperceptible, even with a microscope. But 27 proton widths? Come on, that's like quarter the width of an atom. We're talking big stuff here. Even using an electron microscope, the finest tool of visualization we have, we're still limited by the size of the electron, which itself is easily larger than the smallest particles we already know exist. But maybe we're asking the wrong question again. If we can't observe the smallest object or gradation of space, can we deduce it? What if we used algebra to work from a number we know to arrive at a number we don't? Let's use the infamous d equals r over t equation. If we set our d value to equal the smallest possible distance, then all we need to do is fill in a speed and a time that we know to arrive at our smallest possible distance. Now, the only way to assure that we've arrived at a correct solution is to use as foundational numbers as possible. So if we work from the fastest possible speed to the smallest possible distance, we'll know that we've made it to a correct solution. Now, that takes care of speed, but we've got to find some way to relate that to space. So for that, we'll use g, the gravitational constant. It's nothing special. It's just the factor by which matter attracts other matter, thus bending the fabric of space-time itself. Now all we need is a way to relate these two numbers. For that, we're going to need the research of a brilliant physicist, Max Planck. Planck and his colleagues were studying black bodies, a special type of particle that absorbs all energy to hit it, rather than reflecting some of it, like most substances we're familiar with. The older equation, Wien's law, was accurate to a point, but after a while, the experimental data in the equation began to diverge. Applying the new concept of quantization, that is, assuming all of reality is discrete and discontinuous, Max Planck got much more accurate results and developed a new foundational constant for modern physics, the Planck Constant. This number relates the smallest possible increment of change with photons either receiving or emitting energy. With these three values, the speed of light in the vacuum, the universal gravitational constant, and the quantization of energy, we can apply Max Planck's research into the smallest gradations of energy and find the smallest gradations of space. With a little bit of calculation and careful handling of units, we arrive at this equation, which evaluates to 1.616255 times 10 to the minus 35th meters, the Planck length. This is the smallest unit of distance that makes any sense. Now, to find the amount of space we're looking for, all we have to do is move into the third dimension. So we just need to take that Planck length and cube it. This brings us to what's known as the Planck Volume, 4.2217 times 10 to the minus 105th power meters cubed. This is the smallest possible space. That's pretty small. In fact, if we had an object that perfectly filled that smallest possible space, we could fit 2 trigintillion of that object inside of a grain of sand, and over a trevigintillion of them inside of a hydrogen atom. That's the smallest atom that exists. As unfathomably small as this object would be, we can call it our smallest possible object because it perfectly fills the smallest possible space. Even if a theoretically smaller object existed, it wouldn't make much of a difference because it would still be operating on an order of the smallest possible values or changes. If life is a board game, the size of your pawn doesn't matter if you're only moving one space at a time. While Planck's constant can be applied in so many different ways, I think that's enough for today now that we've answered our question. For now, get out there, keep wondering, and stay curious, my friends. Hey guys, hope you liked this video. If you did, go ahead and hit the like button down below. Let me know I'm doing something right. If you had any questions I didn't answer in this video, or any questions you'd like to see addressed in a later video, go ahead and drop them in the comments section down below. If you'd like to keep up with the latest from the Curiosity channel, go ahead and hit the subscribe button and ring the bell. That'll keep you notified every time something new comes out. Thanks again, guys, and I'll see you next time.